Hey, so this is a short module just to talk about Poisson regression because it's another popular regression technique. You won't actually be quizzed on this. This is just, something in the final project, which I'll talk about in the next module. You can just discuss or, just something that you're aware of that's out there. So this is mostly going to deal with interpretation. And it's just another kind of specialized type of regression here. So here I have module 6, lecture 2, that's Poisson regression. Poisson distributions, it's for count data, 0, 1, and 2, or 3 or 4 or 5. You can model like number of kids you have as count data, white blood cell count, number of times you've been in a car accident, those kind of things. So this is what this looks like. R plus you can actually do to do this, and mu is the mean count here. So number of accidents at a given stoplight, number of children someone has, white blood cell count, number of adverse event, years until retirement, all of those things. They're all count variables. So simple Poisson regression. So we model the mean, mu, which is their expected number of times that this event happens for each person. So each person, maybe I want to predict how many kids they have based on education, family history, those kind of things. So another example, maybe I want to know, maybe there are more wrecks in the summer in a Florida intersection because people are traveling. So let's assume this model here is log of mu. Again, this is my count. My expected count is beta 0 plus beta 1 xi. Why do we model it log of mu? We model it log of mu because exponent of anything is positive. So it's got to be a positive expected count. It's similar why we do the logit transform. This is the Poisson likelihood. Again, I'm not really concerned with you knowing this. All I want you to know is that in the background, this is the formula, and it's the product over I equals 1n. So you multiply them all together, where we find the beta 0 and the beta 1 that maximize this whole function here, okay? And then I plug in beta 0 and beta 1. So as an example, this is an example from a professor in Florida. So basically what he did was he was going fishing for horseshoe crabs, big scary looking ones. And he was looking around each crab and counting how many male crabs were nearby. So I guess generally the horseshoe crabs, the females, they attract a lot of mates, and they usually have males kind of just around them. So we want to know if the bigger a female crab gets, the more males that they can attract. So our Y here is going to be the number of satellites around them. Our X here is going to be the width of the crabs. So this is what the data looks like. This is split up into multiple data sets. So just to highlight, this is your first set of data. This is your second set of data. This is your third set of data. This is your fourth set of data. So this crab, right, they have a color of 2. They have a spine of 3. They have a width of 28.3, a width of 3.08, and they have 8 satellites. This crab here has a color of 3, a spine condition of 3, a width of 3, a weight of 2.6, and 4 satellites. So this is just what their data looks like. And you can see here on this plot here, the scatter plot. This scatter plot is actually plotting the number of satellites here on the y-axis and the width on the x-axis. And if you have a place where it has 2, that just means 2 crabs had that. So you can kind of see like an increasing pattern, kind of, right? That increasing the number of crabs increases your weight. Whenever I actually fit this logistic regression or Poisson regression, I get these estimates here. And here, the exponent of this coefficient is just like an odds ratio here. It's instead is a multiplicative ratio. So that means if I expect to have 20 crabs for a given crab, and they increase their width by 1 centimeter, then that means that that's going to increase their expected number of crabs of 4 times 1.17. So it's a multiplicative effect. It's like an odds ratio, but it's a ratio of expected counts. So this is just me simulating example in R, and I just want to show you that this actually works. So the goal here is to predict the number of hospital visits over the next year based on female identified gender, age, and whether or not they have chronic conditions. So all I'm doing here at the top is generating fake data. So here I have 1,000 patients that I'm generating. I'm generating Poisson distributed age data. I'm generating female yes, no indicators, and I'm generating a chronic illness indicator. So this is all my data. Age is actually a vector. Female is a vector of 1s and 0s. Chronic's a vector of 1s and 0s. I'm randomly generating the number of visits by doing it this way. So I am actually using the linear predictor. So I'm plugging in, right, a true relationship here in this kind of, example. I'm basically saying, hey, look, sorry, the true model here, the true model predicting the expected counts. So the true model log of mu of x, this thing is equal to, I've got a 0 plus 2 times the chronic condition. Yes, no, do they have a chronic condition? Plus 0.02 times their age. So that means, right, that whether or not their gender has no impact, right? So you can see the coefficient for gender here, coef for gender equals 0. I'm simulating that data. This is the data I get. And on the next slide, I'm actually going to fit the data. So I fit the data, do visits to age, female, chronic. And what you'll notice is something kind of amazing. So age, right? What's my true coefficient? My true coefficient is 0.02. And my estimated model here is pretty dang close, 0.017. My female coefficient is 0.048, which is somewhat close to 0. And my chronic condition is 1.99, which is just about at 2. Now, what are my results? My results say that age significantly increases because this estimate is positive, my overall hospital visits. I see chronic condition significantly increases because it's positive, chronic or hospital visits. However, since the female coefficient is non-significant, there's no effect of female gender on number of hospital visits here. Now, usually I don't know the truth here. Here I know the truth just because I generated the data that way. And what this is to show you is if you get enough data, you can actually kind of capture the truth of what's going on. What about the multiplicative effects? Well, I can get at this by doing x of M1 coefficients. That's these values right here. And I can also do x of confident of M1. So that will give me the confidence interval for my multiplicative effects. So my multiplicative effect for age is 1.01, which means every time that I increase age, that increases the expected number of visits by 1.01 times. And this is my confidence interval for that quantity. I also have information on females. They don't have more visits than others since that confidence interval contains 1, right? Just like in odds ratios. And patients with chronic conditions have 7.33 times, this is my confidence interval, 6.89 to 7.0, as many visits as those without after adjusting for age and identified gender. And that's it. And again, right, so just kind of, walking through the assignment, what you're going to want to do is I actually have, kind of a data set pulled up right here, I think. So here I have, let me pull something up. So here I have this data set here, and I can just, kind of show you how I deal with this. So I have this data set here. If I run all the way through, my data set here, it's called KSVTE. I can actually give you code to read this in. So I have KSVTE, and I want to predict y equals data. I'll call it VTE. Occurrence of VTE event equals yes. So what does this variable actually look like? Here I've got head of data. I'm just looking at, information. Hey, does this person have a VTE over time? And I have different information like race and all that kind of stuff. So here I have this. I have my data. And let's create a logistic regression model just as kind of how do I do this as far as the homework assignment as an example. I can say GLM, Y given data. Let's do maybe, I don't know, what are races here? I could say table, data, race. So race here, I have a whole bunch of information. Maybe I just want to know African-American versus others here. So I can say data race equals this. This would be Black or African-American. And let's add age too. So do I have age at diagnosis? So I have these two variables, and I want to add a family equals binomial. So this is going to be my data that I read in. I'll say read it in, and I can say summary of M1. So now that I've read in my data, I can look at it, can look at the results. And what do I see? Okay, I see that there is a differential risk in VTE. This is venous thrombosis embolism for African Americans. And because that coefficient is positive, this is a real data set. African American patients in this data set were at a higher risk of VTE than non-African Americans. I can look at age. I see the p-value for age is not significant. So age has no impact on this risk. So it's easy as that. If I had a Poisson variable here, so what do I have? Do I actually have one? Data age. I can do data age, predict age instead. I could say data age. Let me actually keep this here. I can do a Poisson regression. I could say M1 equals GLM. Let's do it in the opposite way. I'll say I want to predict age as a function of their race, Black or African American. And I also want to add, just as an example to kind of finish this out, I also want to add my Y here. So my Y is, now I'm predicting, hey, does venous thrombolism, is that associated with a higher age? So I need to change my family to Poisson, 2 S's. So if I run this code now, oh, why am I getting something weird? Oh, I need the formula symbol. Here's my symbol. It runs, and I can look at the results, summary M1. So for this data set, and let me put scratch. Bsph, module 6, scratch M6. So if I run this code here, just to give you an interpretation. So here, Y here is my venous thrombolism. So here I see that that doesn't have an impact on age, and neither does race. And that kind of makes sense, right? Really, age should be predicting VTE and not the other way around. And it also makes sense that race and age are not associated here for this data set. But it could happen that way if, for example, in this data set, you were only enrolling people that met certain criteria. So maybe you would unintentionally be discriminating. So it's just examples of how to read the data and just a quick kind of how to do a logistic regression. And I'll upload this too. And remember, right, I can still look at, I can do a test for these things too. I can, do a chi-square.test. I can do table, data race, Black or African American. And I can look at, Y here as well. So this is help for the homework as well. So here I get a small p-value. They are associated. There is a significant association. And we also saw that in the logistic regression, right? In the logistic regression that I looked at, African-American patients had a significantly increased risk of VTE. So there is a dependency there, and you can see that in the chi-squared test as well. Okay, that's it for today. This is going to be the help for the 6th homework, so please watch this lecture.